Hello everyone, today is the day 5 of the 6th week of this lecture series. So let's quickly recap whatever we learned in last class. So we took an example of naphthalene to illustrate all the knowledges about SALC formation using the projection operator, and ultimately utilizing those SALCs to form the energy state of the molecule. So essentially the molecular orbital of naphthalene molecule. So what we did, let's go through that quickly before we move on to our next lesson. So first we figured out the point group of the naphthalene, which is D2H, and then we took the 10 p pi orbitals sitting on 10 carbon atoms. So using those 10 p pi orbitals, we formed an irreducible representation, which is gamma. Okay, so we also said that we can actually separate this p pi orbitals into 3 different sets, because this different carbon atoms forms different sets of equivalent carbon atoms. So we therefore made set 1, set 2, set 3 comprising 4 and 2 p pi orbitals, and individually we form the representations of using the basis set 1, 2 and 3, and ultimately we reduce them and we got the irreducible representation, to which we found the irreducible representation that occurred within the irreducible representations that we formed out of set 1, 2 and 3. And we also said that either way, that is you form the separate 3 representations and then ultimately reduce it to the irreducible representation, or you take all the p pi orbitals, form a representation which is 10 dimensional, and then reduce it. The result will be ultimately same. So after you do that, you use the projection operator for each individual IRs that are obtained, and you find the SALCs. So we saw that there are certain number of irreducible representation occurring. For example, like AU irreducible representation occurs 2 times, B1U occurs 3 times, B3G occurs 3 times, while B2G occurs 2 times. So that means that I will have total 10 molecular orbital, which are given by these SALCs that we have formed, and these 10 SALCs will have their own energies. So in the next step, we are supposed to find out these energies. So how did we do that? We formed the secular equations in terms of the secular determinants, and here in this case, because we formed this individual sets, and from there we found that essentially 4 individual irreducible representations are there, and correspondingly we had like 2 or 3 number of SLCs which transform according to the particular irreducible representation that we ultimately found. So we get this secular determinant to be a block factored determinant, and we took out each block and then form 4 individual secular equations in terms of 4 individual blocks, and solving that utilizing Huckel's approximation, which says that the interaction energy between 2 orbitals are 0 until unless these 2 orbitals are adjacent to each other. Okay, and that energy of this interaction is expressed in terms of beta, and beta is the unit of energy here, and the interaction with itself, that is phi I h phi I, this quantity is written as alpha, and alpha is taken to be the 0 of energy according to Huckel's approximation, and the interaction the overlap integral, that is phi 1 phi 2 integration over all the space is taken to be 0 under Huckel's approximation. So utilizing that, we could find out all the energies of the 10 different SLCs that we can have. So, ultimately we found the energies of the possible MOs to be like this. So, two SLCs which has the same symmetry, AU has two different energies, all right. Similarly, for B1U and B2G and B3G, we found a number of energy levels. Now, our job was to arrange these energy levels, correct. So, beta is negative. So, therefore, the ordering of energy is done in such a way that is shown on your screen. So, these are expressed in terms of beta, and beta itself is negative. So, overall this energy here is negative, and 0, as we mentioned, corresponds to the energies of the atomic orbitals which are not interacting. That means, before the formation of the molecule or the bonds, whatever the energies the atoms have, they are taken to be the 0 of energy. And whenever there is an interaction, favorable interaction, we have lowering of energy, which is given here. So, these are expressed in terms of beta. So, beta is negative. So, overall these energies are all negative, while this terms here, that is minus 0.618, that is also expressed in terms of beta, which is negative. So, overall this is a positive energy, correct. So, these are higher energy. In the next step, we are supposed to fill out these energy levels using with the electrons. So, there we utilize the Hund's rule and the exclusion principle. So, what does that say? That this in case of the order of filling of molecular orbitals for the ground state of a molecule, it follows the same rule as does the filling of atomic orbitals in the ground state of an atom. So, an electron will go into the lowest unfilled level subject to certain restrictions. What are those restrictions? The only 2 electrons may occupy a single level, and their spins must be opposite. That is the exclusion principle, right? Pauli's exclusion principle. When electrons are to be placed in a pair of degenerate orbitals, suppose you have 2 orbitals having same energy, we call them as a degenerate orbital. So, if you have to fill that, so you have to fill both of them having the same spin, so that overall the total spin becomes 1, so which is the Hund's rule, right. So, using this exclusion principle and Hund's rule, we fill out this energy levels. Now, after getting this overall molecular orbital picture and their energies, next we will talk about the this interaction between different energy levels, meaning the transition from one electronic level to another electronic level and the corresponding selection rules. So, we will stop the discussion right here about this molecular orbitals and the corresponding electronic levels and their transitions involved between the electronic levels. We will come back to this after a while. So, in the meantime, what we will try to look at is to look at certain internal motions of the molecule, the bonds, and specifically we will deal with the molecular vibrations, the normal modes, and we will try to see how symmetry properties of the molecule can be applied to molecular vibration to find out the exact normal modes, their symmetries, and their many vibrational transitions or Raman transitions, their probabilities, and the corresponding selection rules. So, this is what we are going to study for another 5 or 6 lectures. So, to start with, if I take any given molecule, they will have 3 different ways to store their internal energy. So, one is translation, rotation, vibration. So, if I have a molecule having certain atoms and then certain bonds there, so this bonds can move in any particular direction, or by changing an angle with respect to another bond in such a way that this motion will not displace the molecule in a particular direction. That means it will not lead to any translation motion. That is, there will be no movement of the center of mass of the molecule. And also this type of motion that I am talking about, that may not change the net angular momentum of this molecule, meaning that there will be no rotation. And such motions of the bonds in a molecule is known as the vibration. Okay. So if I take any particular molecule and consider the internal motions of this bonds or atoms, we can see that there are bonds are moving in different directions, or changing the angles. So like for example, if I take just water molecule, so I can see this OH bonds can move in different way, okay, or it can change its angles. Apparently it may seem that all these motions are very much random, but if you take a close look at that, observe it, you will see that nothing is random, but they are well, this motion is very much regular. The moment I say some motion is regular, that means that there must be some symmetry into it, right? Because in the very first class, if you remember, we said like what are the meaning of this word symmetry. One of these things is there must be some regularity in whatever the phenomena or in a process or in structure. So sometime it may be that this regular regularity in this motion can be a bit time taking, so that apparently it may seem like that there is no regularity, but actually there it is. And how do we classify this particular vibration? Because there may be several bonds are moving, executing vibration, and all of these can be is actually superimposed, and then we get an overall internal motion of this bonds in a molecule, and these are actually quantized by the so-called normal modes. Okay. So many of us are familiar with terms like for a given molecule that there is a stretching, or there is a bending, there is symmetric stretching or asymmetric stretching, or in plane bending, out of plane bending. So these are all actually the individual normal modes, and we will be dealing with these normal modes to find out about the molecular vibrations and their associated properties of this molecular vibration. Now, first and foremost thing is that how do we find out what is the number of normal mode in a given molecule? And probably many of you already know the answer, okay, because many times you get a simple formula, and then you just use that formula and get the number of normal modes that is possible. But many occasions you do that without actually knowing the reason behind this formula. So if you take any given molecule, say for example, I will take a very simple example. Say I have ammonia. Okay, so each of this bond can execute certain motion, okay, such that this doesn't lead to any translation or rotation. Now what I can think of that for each and every atom will have their coordinates, correct. So x, y and z, this is true for each and every atom on the molecule. Now each coordinate is independent of the other coordinates. So therefore this n can move in the x direction by certain amount without worrying about what is going to happen in y and z direction, and h also can do the same thing, and it can do it in any direction. It can do it in the z direction or y direction or in x direction, which are all independent. Now suppose a situation when all the atoms starts moving in x direction by a definite amount, fine. So what happens in that case? You are moving the center of mass in x direction by that definite amount, meaning the whole molecule is translating in x direction by a definite amount. So I can do the same thing in y direction as well as in z direction. So each of this directional motion will give me one translational degree of freedom. So in x and y and z direction I get translational motion, right. So this three directional three individually individual direction of motion will give you total 3 translational degrees of freedom. Now if I think about motion of this atoms in an angular path about either x or y or z axis. Now if all the atoms start executing this angular motion about one particular axis, say x axis, then that will amount to the rotation of the whole molecule by a definite amount, right. So it can be about x axis, separately it can be about y axis and z axis. So this 3 different angular motions about 3 different axes are 3 rotations. So I have 3 rotational degrees of freedom. Now overall how many I have? So I said that each and every atom can execute certain motion in either x or y or z direction, okay, or all together it can do, and all 3 motions will be independent of each other. Therefore if I have n number of atoms, so total number of motion directional motions that can be executed by this whole molecule will be 3n, right. 3n is the total number of motion possible, that is total number of degrees of freedom that it can execute. So therefore I have 3 translation and 3 rotational, so the rest should be the vibration. So I have total 3n minus 6 number of degrees of freedom left for the molecule to execute vibrational motion. So that's how we get this number 3n minus 6. Now this is in general for any molecule, but when we consider a linear molecule, so for example suppose I have the case of carbon dioxide, this is a linear molecule. So here each and every molecule can execute translation in x or y and z direction. So the molecule can have 3 translation motion like this. When I talk about the rotation, then it can have about this axis, it can have a perpendicular axis to this, but there is no meaning of having a rotation about this axis because all the nuclei are contained by this axis, okay. So I have essentially 2 rotational motions. So instead of 3 here I have 2 for linear. molecule. So therefore, for linear molecule we have 3n minus 5, okay, for linear. All right. So let us take some definite example. So this suppose I have a nonlinear molecule and I have 3n minus 6 number of vibrational degrees of freedom. So each of these vibrational degrees of freedom is expressed by the normal vibration or normal modes. So we will take an example of a planar molecule, that is carbonate ion. So we will be talking about CO3 2 minus. Okay. So if I represent this carbon and oxygen by this circles, then I can take this to be my carbonate ion. Okay. So the central part is the carbon and then 3 oxygens are there. So I will have total how many? There are 4 atoms, so 4 into 3 12 minus 6. So I will have 6 number of degrees of freedom. So let's see how this normal mode actually look like. So I'll first have 6 structures of carbonate ion, and then we will look at their normal modes. Okay. So take that all the bonds are actually identical. Okay. So I have got total 6 number of structure to show 6 vibrational normal modes. Okay. So say first mode is I will use a different color to exemplify this. So is this color visible? Okay. So this arrows, okay, so 1 2 3 arrows, they say signify the direction of the movement of the atom, right. So also the the length that we provide to these arrows, they signifies the amount of the movement, though it is quite a bit of exaggerated. Okay. Now let us draw all the other modes, then it will be lot more clear. So here okay, so these are given as sign, so plus and minus. I will explain what this sign means. Okay, and so we need to understand the exact meaning of these arrows, their lengths, their from where they are originating, and all these things in order to understand these motions properly. And then the last one, okay, and we will also give these motions because these are some vibrations. So, they will have their associated frequencies. So, we will have nu 1 and maybe we will write it here. This is nu 1, this is nu 2, this is nu 3, and we will call this nu 3a. There is a reason for doing that, we will talk about that, and this is as nu 3b. And then we have nu 4a and nu 4b. All right. So, now here we have mostly this motion showed by arrow, and in one case it is shown by the plus and minus signs. So, now you can see that in many of this normal mode picture, the arrows are having different lengths. So, what does that mean? Suppose here you have a longer arrow compared to the arrow which is sitting on this central carbon. This meaning that this atom over here, this oxygen is moving in this direction without worrying about what is happening to the rest of the molecule, while this carbon is also moving in this direction, but the amount of movement in that particular direction by this atom and this atom are not equal, and the length, the ratio of this length is actually the ratio of the amount of movement that two individual atoms are making in a particular direction. Okay. Now, as I said, these lengths are quite exaggeration, because these atoms do not really move this much, which are comparable to the bond length. Okay. So, this is just to make things bit prominent to you, and here this plus and minus sign, this mean that this particular atom, it's coming up above the plane of the board, while this oxygen is coming above the board, and this carbon atom is having the minus sign, means that it is moving down the board. So, this is an out of plane motion, while all these things, all these other structures, that nu barring nu 2, all the other motions are in plane. That is, this molecule is a planar, and all the motions of these atoms are within the plane. So, these are in plane vibrational motion, while this is out of plane. All right. Now, one thing you should notice that many cases we have a misconception about how to draw this normal mode. So, here if you look at carefully, the arrow starts from an atom, okay, and goes to another particular direction. So, this particular thing means that this atom is moving. In many cases, you will find that people write the motion in a way like they write like this, okay, or this or this. This is completely a wrong way of representation. So, when you want to present the normal mode, you exactly have to do it in this way, that you start on that particular atom and then put the arrow in the direction into which it is executing the motion. All right, and you have to take care of the relative length of the arrows within a particular normal mode. Fine. So, for example, if you look at this one or this one, this is very clear, or this one, right. So, that will tell you that by which amount one particular atom is moving in a particular direction relative to other atoms within the molecule. So, now here looking at this, I can have two very important properties of these normal modes. Okay. So, these are the normal modes, these are possible. Now, right now I am just drawing this on the board, but how can I get this one? Suppose I draw some arbitrary motions with arbitrary arrow direction. Will I be able to tell that okay, this is the right normal mode or not? So, that must have certain rules, okay, and these rules are governed by the symmetry and group theory. And in the following lessons, we will learn how to actually use group theory to find out the exact normal modes, right? Now, before ending today's lecture, I will mention two important properties of these normal modes. One is that each of the vectors, so all these arrows that we are using, I said that they have a definite length, and they have of course the direction. So they are the vectors, okay, vectors of motion. So each of this vector representing this instantaneous movement of these atoms, and they are giving their displacement, they may be regarded as the resultant of three basis vectors. So we can consider each of this atom having their own Cartesian coordinates x1, y1 and z1, and then we can think of this movement in a particular direction by a particular amount to be the resultant of these three basis vectors, right? And second thing is that, which is extremely important to us, that each of this normal mode, they form a basis for an irreducible representation of the molecular point group. They may form the basis by themselves, or they may actually belong to one of these IRs of the molecules. So therefore, the structure that I drew, they will be assigned to particular irreducible representation. So just for your information, if I put, so this one will form a representation of A1, this one will form the representation of A2, while the nu 3A will form the representation E prime, 3B will form the representation of again E prime, while nu 4 will also form the representation for E prime. So we will do the normal mode nu 4B. So these are the two main points about the normal modes, that is their motions can be expressed by the resultant of three basis vector, and second, that each of these normal modes can form the basis, or not only can, but they form the basis for the irreducible representation of the molecule molecular point group. Okay, so we will utilize these ideas, and then we build on our knowledge about this molecular vibration, their relations with the symmetry, and ultimately having the applications. Okay, so we will come with those things in the following week, and till then, have a good day. Thank you very much for your attention.